Welcome everybody once again. We'll continue with the chapter 22 and we'll be studying the pressure exerted by the gas and kinetic interpretation of temperature. Pressure exerted by a gas. How does a gas exert pressure? As per the kinetic theory, the molecules of the gas are in a state of continuous random motion. They collide with one another and also with the walls of the container. When a molecule collides with the wall of the container, it returns with the changed and equal momentum will also be transferred to the wall. According to the Newton's second law of motion, the rate of change of momentum is equal to the force exerted on the wall, and as a large number of molecules collide with the wall, a steady force is exerted on the wall. The pressure exerted per unit area is known as the pressure. Hence, a gas exerts pressure due to the continuous collision of the molecules with the wall of the vessels. Now, let us derive an expression for the pressure exerted by a gas. We are considering an ideal gas which is enclosed in an elastic cubical vessel containing n number of molecules. Let the dimension of each side of the cube be L. Suppose the sides of the cube are parallel to the coordinate axis as shown in the diagram. If n is the total number of molecules and small m is the mass of each molecule, we are considering a molecule moving with velocity Vx, Vy, Vz, and it hits the planar wall perpendicular to x-axis as shown by A. Let the area of this wall also be A. Now this wall strikes and rebounds back as the collision is perfectly elastic. As the collision we stated in the previous slide is elastic, the molecule rebounds with the same velocity and the x and the component will reverse the sign while the y and z components of velocity do not change. Now the change in momentum of the molecule is minus 2 mvx, and by conservation of momentum, the momentum imparted to the wall in each collision will also be 2 mvx. The distance traveled by the particle parallel to x-axis is between A to A dash, and then rebounding, the total distance traveled is 2L. Now the time taken by the molecule to go to the face and then rebound is 2L upon Vx. The number of impacts or collisions of this molecule per unit time will be L upon delta T, which comes out to be Vx upon 2L. Now as per the second law, F is equal to delta P upon delta T, which is also equal to N delta P upon delta T for the total number of collisions. Now from the equations 1 and 2, we get delta F is equal to mvx square upon L. Force on wall A due to all the molecules will be summation mvx square upon L. As all the collisions are equivalent and the gas is isotropic, the molecular velocities are equally distributed in different directions. Therefore, we have Vx is square is equal to Vy square is equal to Vz square, and if let us name it as V1. So from here we get summation Vx square is equal to 1 by 3 summation V1 square. Substituting this in equation 3, we'll get F is equal to m upon 3L summation V1 square. Capital N is the total number of molecules in the container. The pressure can be written, the force and the pressure can be written as shown here. Now, if you come to the equation lower down, we have P, where m is the total mass of the gas and rho is the density of the gas. Then substituting its value in equation, we get P as rho summation V1 square upon 3n. Since V1 square upon n, which is the total number of molecules, is the average velocity, which is known as the mean square velocity, we define the RMS velocity as under root of summation V1 square upon n, which is known as the RMS or the root mean square velocity. We get the value of pressure as 1 by 3 rho V square, or pressure is equal to 1 by 3 n into m V square. From here, equation 4th, we can get the RMS value of speed also as root 3p upon rho. So the pressure exerted by the gas is 1 by 3 rho V square, where V is mentioned here as the RMS velocity. The kinetic interpretation of temperature. Now, from the previous equation, we had P is equal to 1 by 3 rho V square, or we can also write it as PV is equal to 1 by 3 n into m into V square, where n is the number of molecules. Now, multiplying the above equation by 2 and also dividing it by 2, we get the 7th equation. Now, in this, half mnv square is the kinetic energy of the molecules in the gas. Since the internal energy of an ideal gas is purely kinetic, we have E is equal to the total energy, which is also the kinetic energy, is half mn v square. Now, combining the equations 7th and 8th, we get PV is equal to 2 by 3 times E, or we get P is equal to 2 by 3 into the average kinetic energy per unit volume. If we compare this equation with the ideal gas, that is PV is equal to nRT or PV is equal to KT, we get the equation as E is equal to 3 by T to KBNT, where K is the Boltzmann constant. Now, E upon N, which is the energy per molecule, is equal to half mv square, which is 3 by 2 kT. Thus, the mean kinetic energy per molecule is directly proportional to the absolute temperature of the gas and is independent of pressure, volume, and nature of the gas. Hence, the kinetic energy per molecule is 3 by 2 kT, or the RMS velocity comes out as root 3RT upon m. So V is directly proportional to root T. Faster the motion of the molecules, higher will be the kinetic energy and greater will be the temperature of the gas. Hence, the temperature of a gas is the measure of the average kinetic energy of the molecules. That is what we mean by kinetic interpretation of temperature. Also, when absolute temperature is 0, Vrms will be 0. So we define absolute 0 as the temperature at which all the molecular motion stops.